Alright, so far we've been talking about a branch of calculus called derivatives, and we saw that how that mostly had to do with finding the slope of a curve at a particular point. And now we're going to move on to something called integrals. And so integral calculus is another part of calculus, and we'll see later how derivatives and integrals are connected. But let's start by sort of introducing what integrals are, or like what they try to solve. So let's say we have like a curve that looks like this. With integrals, what we're worried about, or what we want to sort of find, is the area under the curve. So in essence, the integral of a curve on a certain interval. So if I'm measuring this like interval starting at A to the interval ending at B, the integral of a curve on A to B measures the area under the curve. And so this is like a very rough formulation, and it's like very abstract. And later on, we're gonna see how to actually get. We're later on going to develop the tools to actually find out and calculate the exact area under the curve. But before we get to that, a good way to motivate integrals is, let's say you're just given this curve, right? Like let's say I had this arc shaped looking curve. How would I form an estimate of this area under the curve, right? And maybe that will give me a good idea, or a good direction to look at when I actually want to find the exact area under a curve, which is what an integral will help solve. So before we can actually get to integrals, we have to hopefully see like even or formulate a method to find and estimate the area under the curve, and then maybe that will help us solve for the actual area. So one way I propose to go about finding the area under the curve is, let's say again, now I'm just gonna draw out a different looking curve. Let's say I had a curve that looked like this, right? So it's a increasing function, and it's also like a concave up function. If I were to sort of, and so this curve starts at 0, and then let's say this is like a point 10, right? If I were to draw, um, if I were to split this like interval into equally sized intervals of like, let's say size 2, so I had like 2, 4, 6, 8, right? And if I were to sort of draw like a rectangle at those points, and then, okay, please don't mind my rough drawings, but let's say I drew a rectangle, and it's like anchored at the right endpoint, right? So this is 8, and then finally 10, right? Notice how Notice how if we took these rectangles, now we can kind of like calculate the area of a rectangle, right? Because we know what the area of a rectangle is. It's simply the area is just the base times the height, right? And we know that our base, because like what we're doing is we're making rectangles of equal sizes. Our base is always 2 in this case, right? Because we took an interval of size 10 and we divide it into 5 different rectangles. So our base is 2, and our height is simply, so if this curve was like a function x, our height is just equal to f of x, and x is just like the point we're querying. So if we look at this rightmost rectangle, our area would be just 2 times f of 10, right? And if we were to sum up all of these rectangles, the areas of all these rectangles, we can get an estimate of the curve. So we can say like the area under a curve is about 2 times, and then this is the summation notation from I equals 1 to 5, because I have 5 rectangles, and then I'll just say like f of x of I, where x of I is just like, oh, 2, like x of 1 is 2, and then 4, and then like 10, right? So x of 5 is 10, etc., etc. Time, yeah. And so this this is about the area. And so you see that what I did to estimate the area under the curve is I split the entire curve into equal size intervals and sort of drew a rectangle on it. And if calculated the areas of each of those rectangles and summed them up to kind of estimate the area of the curve. We would like a perfect formulation would allow us to take this curve and then, if we again chunked it up into size 2 intervals, right? A perfect formulation would just allow us to create these shapes and find the area of those shapes, right? But the problem is we don't really have a formula or a way of finding the area of this shape because this curve is not like a straight line, or it's not like a shape we know. It's like the curve is determined by f of x, right? This curve over here. We do know this and we know the height, right? But we don't know how this curve behaves. And so there's no real way, at least now, for us to find out that area and how that's behaving. So we have to resort to using figures such as rectangles and geometrical shapes that we're used to estimate the area of the curve. And so this idea of treating each interval as like a small rectangle and then finding out like just multiplying base times the height allows us to approximate the area of the curve. And indeed, this is called something called the rectangular. It's called the rectangular approximation method. And there's actually 3 flavors to this, and they're very similar. So let me first go over something called the LRAM, which just stands for left RAM, and RAM is just this rectangular approximation. And what LRAM means is, let's say I have again, like I had that curve, right? So in each of these approximation methods, what you do is you have an interval from some starting point, and let's just call this 0, and then some ending point, we'll call this 6. And so if we want to measure the area of this curve from 0 to 6, what LRAM does is, well, all of these are rectangular approximation methods, so we'll form rectangles of equal widths in this interval. So if you want to find out, if you want to use LRAM with 3 rectangles, that means each rectangle has all the rectangles have the same width, so our widths are going to be 2. So 2 and 4. So now we have 3 rectangles, and then so they're going to look something like this, or they're going to be anchored at point 2, 4, and 6. And what LRAM means is we take the left point as the height of the rectangle. So previously, when I was like motivating integrals, I was taking the right point, right? And that's something called RRAM. But LRAM just means we take the left point, and that's our anchor for the that's our anchor for the height of the rectangle. So the first rectangle is going to have a height of 0. The second rectangle is going to have a height of whatever f of 2 is, and it's going to end over here. The width's always 2 for all of these because that's just what we decided. We're going to make or the problem was stating that we want only 3 rectangles to approximate. And the last rectangle is going to be anchored at 0.4, and then we go as before and find the areas or the sum of the areas of all of these rectangles, and that serves as our estimate to find the overall area of the curve. And like I was talking about before, RRAM is simply the same process. So if we were to again have 3 rectangles approximate our area on the interval 0 to 6, RRAM just means that the height of the rectangle is just going to be anchored at the right point. So over here, instead of 4 being the anchor for the third rectangle, it's going to be 6. So it's going to look something like that. And the middle rectangle is going to have an anchor at 4, so that determines the height. And the first rectangle is going to have the height anchored at 2. Right? And so notice that depending on what approximation method you use, you get a different approximate of the actual area of the curve, right? Because it is dependent on if we're using RRAM or LRAM. And then finally, there's something called MRAM. And this just stands for, oh, I had an extra M. MRAM just stands for midpoint rectangular approximate method. So this is midpoint. And instead of anchoring at the right or left point, we anchor at the middle point for the curve. So again, if we have a curve that looks like this, and then, we have 3 rectangles that we're using to approximate the overall area. Our third rectangle is going to have a height at the midpoint, and all of them are, so the heights of the rectangle are determined by the midpoint value. So here it'll be f of 1. The middle rectangle will have the height depending on f of 3. And then the rightmost rectangle has a height of f of 5. So these are just like 3 flavors of the rectangular approximate method, and I think like what I'm gonna talk, like at the end, I'm just gonna talk about, like, maybe you guys already noticed some stuff, but depending on the curve itself, these approximation methods can sometimes over approximate or sometimes give an under approximate of the actual area of the curve, right? So over here, like in the LRAM, notice how, well, so the f of x I'm considering is increasing, right? So this is an increasing function. So when a function is increasing and we use LRAM, we are under approximating the area, right? Under approximating the area because we're always anchoring to the left point. But we know that because we're using a rectangle, we're always missing this like this extra area over here that forms because the function is increasing. But when we're using a rectangular approximate, we're not really accounting for that increasing. So that means that LRAM under approximates the area of a curve when we have an increasing function. And likewise, like if we had a decreasing function and we had an LRAM, we would be over approximating because the anchor is higher than like what the function will be afterwards. And then like inversely, RRAM will over approximate on increasing functions and under approximate on decreasing functions. And to notice this, I mean, you just have to use that similar argument as I made for the LRAM's case. And over here we see how the function is increasing, and because our RRAM is anchored on the right point, and we're just treating it as a rectangle, we're keeping this like height constant, but in reality, as you go towards the left, the height is actually decreasing because the function is overall increasing. That's why we have an over approximate. And when the function is decreasing, you have an inverse effect where you're under approximating. And MRAM, but because it takes like the middle value, we kind of take a middle of the way road, right? We have parts of it that are over approximated, but parts of it that are under approximated, because we're taking the midpoint of the 2 values. And so usually, like if you were to do MRAM, sometimes you'd get a better approximate when the function is like continuously increasing or decreasing. And so that's why, like, depending on the property of the function and where it's increasing and decreasing on the interval that you're looking to get the area under, these different approximation methods can have different accuracies. And finally, I want to sort of talk about, so I kind of talked about the relationship between if a function is increasing, decreasing, and how these rectangular approximation methods sort of over or underestimate. But what about the relationship between relation of number of rectangles and accuracy? So notice how, let's say, I wanted to estimate the area between, now I'm just going to use like general variables. I wanted to estimate the area of the curve in the interval of a to b, and let's say the curve looks something like this, right? So this is the interval I am worried about, and let me draw the same, or attempt to draw the same sort of curve on both sides, right? And so I have A and B. Do we think that having more rectangles in this interval will give us a better approximate or less, right? So let's test it out. So let's say here we only have two rectangles to work with, right? And so if we had two rectangles to work with, and let's say we're just using like LRAM to be to keep it simple. So this will be like a plus b over 2. It doesn't really matter what this number is, but because we have two rectangles, right? And we're using LRAM, our estimate is going to just be the sum of this rectangle and this rectangle, right? So over this in this rectangle, there's parts of it that we're overestimating, just namely this portion of it, and then we're also underestimating this part. So we are a bit inaccurate, right? But what if we had more rectangles to work with? And let me just use like 1, 2, 3, 4. So we have 5 different rectangles, right? And if we were to use LRAM, I have this, and then I have this, and then this. Let's say it's just mostly flat, and this is also flat, and then this. Ooh. So notice how now just visually it looks like the amount we overestimate is much lesser. Like this, in this range over here, it's almost 0, and then we underestimate this. So our error just visually looks much smaller than before, right? And this is actually true. As we increase the number of rectangles, so plus number rectangles, what we're doing is we're 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 basically getting closer and closer to like actually estimating the curve and how the curve looks like, because in when we have less rectangles to work with and we're working in larger intervals, we're like kind of treating more and more of the curve shape into like a rectangular shape, and that is clearly not how the shape actually looks like, but we're just doing it for the purpose of estimating the area, right? So naturally we would be having more of an error, but when we have smaller and smaller, like, or when we have more and more rectangles to work with, we can kind of estimate the shape in a much better way, right? Because we're kind of less crudely representing the curve itself. And because we can estimate the shape in a much better way in this case, our estimate of the area will be better as well. So no matter what approximation method you're using, right? LRAM, RRAM, MRAM, and then there's also like other non-rectangular approximation methods as well. But no matter what approximation method we're using, the idea is the more rectangles and more, or like the more rectangles slash, if it's not even a rectangular approximation method, just the smaller the intervals, so slash smaller intervals equals better approximation. And kind of like think to yourself of why this is the case. I kind of like mentioned it where with more rectangle, or with like just smaller intervals of where we're calculating the area over, we are better kind of shaping the curve, right? If we have more, think about like a puzzle piece, right? If we have treat each of these like rectangles as a puzzle piece. If we have more and more puzzle pieces to represent the entire curve, we can better represent the curve because we can like fit different parts of it better, right? If we just had one puzzle piece to represent, one rectangular puzzle piece to represent this entire curve, then it would look like this, or like this whole one big box, right? And that's clearly not doing a good justice to how the curve looks like. But if we had like 100 puzzle pieces, then we can like perfectly fit parts of it, and that will lead to a better estimate. So this is in general a true statement, and this is actually very important when we actually get to finding the exact integral. So this is the last thing I want people to take away from this, where approximations get better as we have smaller and smaller intervals. So smaller intervals equals better approximation, and that is basically the end.